I thank the organizers of ESPO for the opportunity of being here and listening to the exciting talks we have heard so far. My talk is on thermodynamics and economics. When I was a student, I found economics just boring, and I hated thermodynamics precisely for the mathematics I'm going to bother you with a little. Just bear with me. Well, industrial economy consists of a productive physical basis and its market superstructure. Let me get this one, that's better. Yeah. Yeah. Okay. Oh yeah, thank you. Yeah. So it consists of a productive physical basis and its market superstructure. Standard economics is essentially concerned with the behavior of economic actors and their trading of goods and services in the market. This is ruled by the first law of economics. Wealth is allocated on markets, and the legal framework determines the outcome. Sorry, I have to get used to that thing. Determines the outcome. The natural laws that govern the production of goods and services and the productive physical basis have received little attention by mainstream economists so far. Their impact is summarized by the second law of economics: energy conversion and entropy production determine the growth of wealth. The growth model to be considered so far is based on factors that generate the products of the productive physical basis by work performance and information processing. They are capital, labor, energy, and human creativity. The available space comprises the economic system and absorbs the emissions from entropy production. Let us first look into benign energy conversion. Nasty entropy production will be addressed at the end. Energy became an issue of economics and especially of economic theory in the wake of the first and the second oil price explosion. I rather prefer to use this thing, which happened in the 1970s. Here we are. But there was a big debate going on whether these oil price explosions really could have had an impact on economic growth. We had two deep recessions after these first and second oil price explosions because of wars in the Middle East. And there was a debate between Jorgensen and Dennison was arguing it cannot have had any economic impact because the weight of energy is very little. It is about 5% of the total cost of production, and because of this little small economic weight, it couldn't have much impact. But this is based on the so-called cost-share theorem. According to it, the weight of a production factor is equal to its share in total factor cost, and that was has been 5% for energy, 70% for labor, and about 25% for capital on an OECD average. But this cost-share theorem is wrong. and it's wrong because it has been derived by profit optimization or optimization of overall welfare without taking into account technological constraints on the combinations of the factors. And if there is time, I will point out the math of that a little bit more, or we can discuss it later in the following discussion. Well, now, the following is an alternative econometric model of computing the impact of energy on economic growth. The quantities we are considering is output, and the output is, for instance, the GDP, if you consider the whole economy or a part thereof. And it's produced by work performance and information processing. And the factors that produce the output are capital, and capital consists of all energy conversion devices and information processing devices and the buildings and installations necessary for their protection and operation. That's what in the national accounts is the capital stock. It's not money in the bank. Labor manipulates the capital stock, and energy activates the capital stock. And the impact of human creativity, that is human ideas, inventions, and value decisions that affect the output, we just give the name creativity. It can only be measured ex post. In the capital labor energy creativity model, we now consider normalized output as a function of the normalized inputs of capital, labor, and energy. These are dimensionless units, and it's convenient to work with these units. And we assume that creativity causes an explicit time dependence of the production function that is used to describe mathematically the growth of output. And we can compute production functions which tell us quantitatively how output, wealth, depends on the production factors, capital, labor, and energy by solving the growth equation. And this says that the relative growth of output, that is the growth rate, that is the thing the fate of governments depend upon in our days. So this growth rate is the sum of the weighted growth rates of capital, labor, energy, and the change of time. And these weight factors, alpha, beta, gamma, and delta, they are called output elasticities in economics, and these are the key quantities of my talk. And as you see, they give the weights with which relative changes of the production factors and of time contribute to the relative change of output. And in this sense, these output elasticities measure the productive powers of capital, labor, and energy. Now, the standard mathematical requirements on production functions lead to a set of coupled differential equations. They are partial differential equations for the output elasticities. And they have an infinite number of solutions. All have to depend on the ratios of the production factors. So that's what part of the nasty mathematics, but I will not go much more in detail into this. Just say that's what every macroeconomic production function has to satisfy, all the ones that are on the markets. And a very trivial special solution are, of course, constants. And the next non-trivial solutions are written down here. They obey certain technical economic boundary conditions. For instance, the output elasticity of capital satisfies the law of diminishing returns, and the output elasticity of labor allows for the substitution of routine labor by combinations of capital and energy, so that the economy approaches more and more the state of automation as automation increases. Now, with the constant output elasticities, if one inserts them into the growth equation and integrates, one gets the workhorse of economic theory, that is the Cobb-Douglas production function. And mostly the Cobb-Douglas production function, which I have here, does not involve energy, because usually in standard economics one gives the economic weights, the powers of capital, labor, and energy are, as I said before, given by the cost shares, so that alpha, the productive power of capital, is assumed to be 25%, for labor it's assumed to be 70%, and energy just gets a meager 5%. But with this cost share weighting, standard economics can explain not more, at most 50% of the growth that is observed in industrial countries. The rest, the notorious Zoloff residual, is attributed to technological progress. And technological progress is just a word for what one does not understand. It is also dubbed manna from heaven in economic textbooks. Now, if one uses the non-trivial output elasticities, integrates the growth equation, one obtains the one obtains the Linux production function that depends linearly on energy and exponentially on the ratios of capital, labor, and energy. And it has two technologies parameters, which are to be determined by fitting the Linux production function, ordinarily square, fitting to the empirical time series, observing, and that's mathematical challenge with my students mastered, that with the boundary, with the constraints that all output elasticities have to be non-negative. Otherwise, the growth of the output would reduce an input. That's a situation the economic actors will avoid. Now, next I show you the results for Germany, Japan, and the USA. On the left-hand side, you have the growth of capital, routine labor, and energy in the Federal Republic of Germany before and after reunification. On the right-hand side, the black squares indicate the empirical time series of output, and the red dots is the result obtained with a Linux production function, and below the time change of the technological constraint, the technological parameters are indicated. Here we have the same for the industrial sector, that is Warenproduzierendes Gewerbe, which produces about 50% of German GDP. And here on the left-hand side, you see the oscillations of the energy inputs after the first and second oil price explosion, and here you see that output and empirical output follow closely the oscillations of the energy inputs. A similar picture we have for Japan, left the empirical growth curves, and on the right you see the theoretical growth, and observe in Germany labor has decreased, in Japan it nearly stays constant, and now we look into the United States. Here, routine labor has grown all the time with some oscillations. You see the oscillations of the energy inputs, and here the damping of the growth of US GDP after the first and the second oil price explosion. Now comes the core of my message, and this is now economic heresy. What I show you is the time-averaged outputs of the production factors. So the time-averaged output elasticities. And you see here for both German systems, energy, the productive power of energy, is far larger than its cost share of about 5%, while that of labor is much smaller than the cost share of about 70%. We have the same picture in Japanese industry, high productive power of energy, low of labor, and the same is true for United States. And the next slide I skip. These are the statistical quality measures and the arrow bars. If you are more interested in it, we can go into this more in detail. And now this is the point with the equilibrium conditions. How much time is left? 5 minutes? Oh, I skip it and explain it later if you wish to. And I skip that too. And now I come to what really motivated me as a theoretical physicist whose job was superconductivity and semiconductor physics, why I went into economics. And these are the first two laws of thermodynamics. They're written here in one way, and verbally we can say the following. The first and the second law of thermodynamics say that nothing happens in the world without energy conversion and entropy production. That energy conversion plays an important role in the production of material wealth. Well, we are all convinced of that anyway, and I have shown it again with mathematics, which has been borrowed from economics, just save for the treatment of the output elasticities. And unfortunately, now that's the bad part of the first two laws of thermodynamics, which also people call the constitution of the universe. I mean, physicists believe in, well, many things, and they doubt many things. But one thing no physicist doubts at all are the validity of the first two laws of thermodynamics. And because of the second law, and that's the ugly face of these two laws, is that entropy production is always coupled to energy conversion. And whenever something happens in the real world, entropy production is non-negative. It's always the disorder increases. And this entropy production decreases exergy, the valuable part of energy, and increases energy. And furthermore, it is associated with the emissions of heat and particles. And these emissions of heat and particles, they change the energy flows through the biosphere, and they change the composition of the biosphere. And if these changes occur so rapidly that individuals and societies cannot adapt to them sufficiently rapidly, they are conceived as environmental pollution. And since entropy production destroys exergy, this poses limits to the improvement of thermodynamic efficiency. You cannot improve the efficiency of a heat engine below the, make it better than the Carnot efficiency. And this efficiency, there are thermodynamic limits to efficiency improvement. By the way, I should say, no, I say it later. But I may say it to Dennis Meadows because that was very influential in his book, but not now. Now, let's conclude it. Energy is cheap and has a high productive power. Labor is expensive and has a low productive power. And this results in the pressure to increase automation, where cheap energy capital combinations substitute for labor. It also reinforces the trends towards globalization, because goods and services are produced cheaply in low-wage countries, and they can be transported cheaply to high-wage countries. And the consequences are that routine jobs in high-wage countries are getting lost, and the profits increase for the owners of the energy conversion devices and the owners of the energy sources. If you read the World Wealth Reports of Merrill Lynch Bank, you see how the number of high net worth individuals making more with financial assets of more than $1 million increases during all the time, and by now their income is about 3/4 of world gross national product. I should say not their income, but that's their financial assets. And these gain essentially the wealth created by the energy slaves which are working in our machines. Well, the next problem are the climate change problems. I don't have to say much about it. We have heard we have to reduce the combustion of fossil fuels, and we have to do it rapidly, and we all hope that non-fossil fuels, especially renewables, come to the rescue in time. Well, Germany has decided to phase out fossil or nuclear fuels rapidly, and hopefully the world will not learn sad lessons from Germany's Energiewende experiment. The reason for that is the U-turn in German energy policy was very hastily made after the Fukushima accident last year. And haste makes waste, not only in thermodynamic systems, but also in society. In thermodynamic systems, it's the entropy law, and in society, well, these are the turbulences. People react to sudden changes of the frame condition of the market. And right now, German government speaks of a Herculean task which we have to master. A year ago, our Minister for the Environment said, oh, we just will make that by more competition in the market. So this is my last official slide. 14 days ago, I have been asked, how could one model the impact of peak oil? And that's a spontaneous, rather primitive model. Build a three-sector model of the economy that has agriculture and transportation and all the rest. And then describe the outputs of transportation and agriculture by appropriate production functions with the appropriate productive power output elasticities not equal to cost shares but determined econometrically, and then model how the outputs of transportation and of agriculture influence the production of all the rest, and then analyze how reductions of the inputs in the rest, which come from transportation and agriculture, react to peak oil or reductions of fossil fuel consumption because of climate change, and then compute scenarios. So I don't comment on the last slide because I will make many enemies with that, but my conviction is that we will avoid the self-destruction of capitalism we talked about yesterday only if we change the legal framework of the market in a sense that shifts the burden of taxes and labors from labor to energy in a way which is indicated here. Thank you very much for your attention.